So on we go, moving into chapter 6, which, as you can see, is titled Trigonometric Functions. Sorry, that's just me moving some stuff around on my desk. So the first section that we're going to get into, section 6.1, of course, is all about angles and how we measure them, with some applications to measuring out arc length and describing circular motion. Let me hide this little thing. Okay. So what we're going to learn about is how to measure angles in degrees, including subdivisions called minutes and seconds. And then we'll go from there and discuss arc length. So if you measure out a portion of a circle, how do you determine how long it was? That's going to lead us to a discussion of something called radians, another way to measure angles. And from there, we'll talk about area and linear motion. Okay. So first, we have to basically discuss what is an angle. So if you have a single point called the vertex, and from it you send out two directions. These can be rays, they can go on forever, but they don't have to be. They just have to be line segments in directions. Then you measure from the initial side to the terminal side in the counterclockwise direction. Okay, so this is the standard direction of measuring an angle. So if I had said that maybe this was the initial side, then the angle would be measured like that. Okay, always measure in the counterclockwise direction. If you decide that you want to rotate clockwise, that's okay, but then the angle is negative. So many of us, for example, know this is a 90-degree angle when measured in this direction. If, however, I measured it in this direction, I would call it a negative 90-degree angle. So there is actually a rotational direction associated to measuring an angle. Okay, also note down here at the bottom, this last one, it's possible to measure an angle by, say, starting here at the initial side and going all the way around and then coming back here. So this angle, for example, would be 360 degrees, that's one full rotation, plus a little bit. And indeed, you could even do something like this. Okay, over on the left, you could go all the way around twice before measuring it. Alternately, you could do a negative angle that goes all the way around before measuring it again. Okay, so angles can go complete rotations and then some. And what that means is if you just see an angle drawn, let me clear out my marks so I can put some new ones down. If all you do is you see this angle marked and someone asks you what's the angular measure of that, in a sense it's kind of ambiguous because you don't know which direction they want to measure, and maybe there's the possibility of going around several times. However, okay, the standard position of an angle is to assume that you're measuring from, in the counterclockwise direction, a positive angle. And if you have an angle like this, for example, you assume that you're measuring this smaller one, not this bigger one. That's not ironclad. I mean, sometimes we may want to measure angles on the larger side. But normally what you're going to do is you're going to place the initial side along the positive x-axis. That places the terminal side somewhere else, and then you measure in the counterclockwise direction. So if you did want to specify you were measuring an angle like bigger than the other one, so for example, if I draw this and I want to specify somehow that I mean this angle, I don't mean this one, I need to specify that this is the initial side and this is the terminal side. Then you can imagine trying to place it so that on the normal coordinate axes, if the initial side goes here, then the terminal side would go somewhere like this, and then the angle gets measured in that direction, and yes, it's more than halfway around the circle. Okay, so the standard position of an angle is to put the initial side on the positive x-axis and then measure in the counterclockwise direction. If you want to measure in the clockwise direction, that's okay. Just remember that that means your angle is going to be negative. Okay, so a couple of further terms. So we have these quadrants. So in the xy axis, if x is positive and y is positive, that's quadrant 1. If x is negative and y is positive, that's quadrant 2. If they're both negative, that's quadrant 3. And if x is positive but y is negative, that's quadrant 4. Okay. So angles can lie in a quadrant, and the way you specify what quadrant it's in is if it is in standard position. If the initial side is along the positive x-axis, where does the terminal side lie? That's what quadrant the angle is in. Okay, so you can see here are a quadrant 2 and a quadrant 4 angle. If an angle happens to exactly split between two quadrants, not the one I drew because I can't draw it terribly accurately, but the one that actually points straight down along the y-axis there at the bottom right, you can call that a quadrantal angle. That's a term that I've never really heard outside of this little brief introduction. No one really uses it, but we do definitely talk about angles like this being in quadrant 2 or quadrant 4, or quadrant 1 or quadrant 3, whatever. Okay. So how do we measure angles? The standard lay person outside of mathematics way of measuring angles is in degrees. And the specification is that a complete rotation is 360 degrees. Therefore, a quarter of a rotation is 90 degrees. It's 1/4 of it. Half of a rotation, or going on around a straight line, halfway around the circle, is 180 degrees. Okay. Pointing straight down is 270 degrees, and coming all the way back around, one full rotation, is 360 degrees. Notice that 360 degrees is pointing straight right, so that's 360 degrees, but it's the same thing as 0 degrees. Starting your measurement in standard position and doing nothing points directly right, and that would be 0 degrees. So why 1/360? The reasons are historical. So why would we choose to divide the circle into 360 pieces rather than 100 pieces or 400 pieces? So there are two basic reasons behind this. 360 can be very easily divided into half, a third, a quarter, a fifth, a sixth, an eighth, a ninth, a tenth, a twelfth. These are all divisions that break down into whole numbers. So a twelfth of a circle is exactly 30 degrees. Okay. If you had, for example, 100 degrees to a circle, then what's an eighth of a circle? It's not a whole number. So honestly, the divisibility of 360 is a big factor. It's also pretty close to the number of days in a year. So you can measure the Earth's orbit around the sun by saying 1 day is approximately 1 degree. It's not exact, of course, but for a long time it was fairly close. Okay. So otherwise, just look at these diagrams down here. As I mentioned, if you go all the way around, that's 360 degrees. A right angle is 90 degrees. A straight line measurement is 180 degrees. So how would we draw each of the following angles in a standard position? So pause here, try to draw these, and then we'll go through and work through it. All right, hopefully you gave it a shot. So 135 is 90 plus 45, and 45 is half of 90. So we do a full right angle and then halfway to the next one, and that's 135 degrees. Negative 180 degrees, well, 180 is a straight line, but we want to measure it in the negative direction, so we go clockwise. 90 degrees is exactly 1/4 rotation. That's our right angle. We typically mark right angles with this little square measurement, and that's like, even if I draw it pretty poorly, if I put that in there, I say, heck, I meant for that to be a perfect right angle. And 495 degrees, notice, is 360 plus the angle we already did. So we already had drawn this angle here, and that's supposed to be a straight line, sorry, of 135 degrees. So this just says go all the way around 360 and then 135, and it points in the same direction. Okay, so 135 is the same angular measure as 495 degrees as far as where it points. Okay, so suppose you need to start dividing degrees into smaller units. It's perfectly fine to write things like 8.28 degrees. You can use decimals, that's okay. There's actually a standard that's still used in nautical navigation, like navigating ships around and airplanes, where the subdivision for degrees are called minutes. There are 60 minutes in 1 degree. So if you have a very, very small 1 degree measurement, if you break it up into 60 smaller pieces, these are called minutes. And then if you have a very, very tiny 1/60th of 1 degree, in other words, so what's 360 times 60? Because there's 60 degrees in a circle, sorry, 360 degrees in a circle, and 60 minutes per degree. So we've got 2,160 minutes per circle. So if I take a 2,160th of a circle, and there's 1 minute, if I divide it into 60 pieces, those are each called seconds. Okay. So how would you convert 65 degrees, 9 minutes, and 17 seconds to a decimal quantity of degrees. So notice what we have here is we have 65 degrees, then we also have degrees, sorry, we should mark our units. 65 degrees, plus we have 9 minutes, and then we also have 17 seconds. Now, how many degrees is 9 minutes? It's 9/60ths of a degree. 17 seconds is 17/60ths of a minute, but 17/60ths of a minute, sorry, not degree, minute, 17/60ths of a minute, I keep writing the wrong symbol, sorry. So let me start that over, and I'll keep my symbols straight this time, I promise. So what we have is 65 degrees, then we also have 9 minutes, then we also have 17 seconds. But we have some conversions we can do, okay? For every 1 degree, there is 60 minutes, and for every 1 minute, there are 60 seconds. So these are conversion factors using units. Degrees, 1 degree per 60 minutes, 1 minute per 60 seconds. So I want to be in degrees, that's fine. So I'm going to take this 9 minute, and I'm going to say, I'm going to multiply this by, there is 1 degree per 60 minutes. Then the 17 seconds, I'm going to say there is 1 minute per 60 seconds, and there is 1 degree per 60 minutes. And now my units start canceling, okay? These minutes cancel those minutes, seconds cancel seconds, minutes cancel minutes, and everything is now left in degrees. So we have 65 degrees plus 9/60ths of a degree plus 17 over 60 times 60 of a degree. Okay, I'm going to clear out my writing because the book is going to show their way of working out the solution. You just have to get a decimal approximation of this. Oh, sorry, there was a second problem. Convert 32.479 degrees to minute-second notation. So for this first problem, okay, notice they're saying 1 minute is a 60th of a degree and 1 second is a 60th of a minute, which is a 60th of a 60th of a degree. So we end up with exactly the conversion that we had on the previous slide, which if you evaluate it works out to be 65.1547 degrees. Okay, part B said, sorry, I forgot the quantity that was involved. Let me slide back, 32.479. So for part B, we're supposed to convert 32.479 degrees. We're supposed to convert this into minutes and seconds. So here's how I do it. Okay, so what we have is we have 32 degrees, and then we have 479 out of 1,000 degrees. That's just converting the decimal 0.479 into a fraction. So what I need to do is I need to ask 479 out of 1,000 degrees is how many minutes? Okay. Now what I know about minutes is that there is 1 degree per 60 minutes. So if I just multiply both sides, by 60, what we end up with is 60 times 479 over 1,000 is how many minutes we have. So if I compute that, just pulling out a calculator off screen, 60 times 479 divided by 1,000 is 28.740. 28.740. So I'm going to replace, over on the left-hand side, I'm going to replace the 479 over 1,000th degree with 28.740 minutes. Now that's 28 minutes and then 740 thousandths of a minute. Okay, so I'm just going to do the same thing again. I'm just going to bring out the eraser so I can erase this work without erasing the other half of the slide. So now I just need to convert 740 thousandths of a minute into seconds. And I'm just going to do the same work. Okay, if I just multiply it by 60, there's the pen. So we have 740 out of 1,000 minutes is how many seconds? Well, for 1 minute, there are 60 seconds. So if I multiply both sides by 60, we get 60 times 740 over 1,000 is how many seconds this was. And again, I'm just going to pull off a calculator on another screen and do 60 times 740 divided by 1,000, and it's 44.40. So I'm going to replace the 740 out of 1,000 minutes with 44.40 seconds. Okay, so this is just converting back and forth between units. And again, I'm going to erase all of my work because the book is going to show it the way they did it. So they just pull off that decimal point there. That's 0.479 times 1 degree, but 1 degree is 60 minutes, which is 28.74 minutes. Then they pull off the 0.74. 1 minute is the same as 60 seconds, which gives us exactly the same answer. Okay, I think they said to 2 decimal places, in which case you should write 44.40 seconds. Okay, so there it is in degree, minute, second notation. And in navigation, people still measure headings in this way. They say, go on a heading of so many degrees and so many minutes. Okay, so that's just a basic primer on what an angle is and how we measure them. I wouldn't worry too much about the minutes and seconds part unless you are planning on going into a career in like navigating cargo ships or something. So typically we're just going to measure them with decimal approximations and consider that good enough. Like I don't write minute degree notation. At worst, I'll say something like 12.28 degrees and just consider that good enough. But the actual real message is we tend to not actually use degrees to measure angles anyway. So when we come back in the next video, we're going to start studying arc length, and that's going to lead into an entirely new way of measuring angles.